Hi, today we're going to speak about some elementary combinatorics which is going to lead into the binomial theorem. So we're going to start very gently with a really easy example. So let's suppose we have a set with 3 elements. Okay, how many ways can we order the elements of this set? Well, we've got ABC, ACB, BAC, BCA, CAB, CBA. So there are 6 choices. But where did this 6 really come from? Well, we started with 3 choices, right? Once we fixed our first choice, we were left with 2 choices. Okay? And once we'd fixed 2 choices, we were left with 1 choice. Okay? So this is 6. Okay? So there are 6 ways to order 3 elements. Okay? So 6 orderings. Okay, so now a slightly tougher question. How many ways can we order the elements of a set with n objects? So we've got a set with n elements. Well, if we're interested in orderings, just like above, we start with how many choices? Well, of course, we start with n choices, okay? So once we've fixed one of our choices, we're left with n minus 1 choices. And of course, we go down with n minus 2 choices, n minus 3, etc., all the way down to 1. So we've got n by n minus 1 by n minus 2 by ... orderings of a set with n elements. Great. So it's a little bit messy to write n by n minus 1 by n minus 2 ... So we introduce some very neat notation. So we define n factorial to be n by n minus 1 by n minus 2 all the way down to 1. Okay, good. So what about if we wanted to choose k elements from this set and see how many ways we could order them? Well, so if we wanted to order k elements, we would start with n choices. So we fixed 1. So our second choice, we have n minus 1 elements. How about our third choice? Well, we've got n minus 2, all the way down to n minus 1 plus k. Okay? So we've got this number of ways of ordering k elements from a set with n objects. Okay, nice and easy. So this is all about ordered choices. So now we're going to move on and have a think about unordered choices. So back to our original set. How many ways can we choose 2 elements from this set? Well, this is kind of easy, right? Of course, we can choose AB, AC, and BC. So it's different from last time. So here the ordering doesn't matter. right? So if order was important, if it was, of course, we would also have BA, CA, and CB. But it's not important. So we only have 3 choices so we only have 3 ways of choosing 2 elements from a set with 3 objects. Okay, so let's think about generalizing this. Okay, so now a slightly trickier question. How many ways can we choose k elements from a set with n objects? Well, let's just think about that. So we've got A1, A2, all the way up to AN. Well, if we look back at this set with 3 elements by analogy, we can see something sort of very nice going on. We can see, well, if we consider the set of ordered choices, okay, we get 6. But we have to identify all the different orderings of the same set together. So what does that mean? Well, it means that we've got n by n minus 1 by n minus 2 all the way down to n minus k plus 1. Okay, so we know this gives us all, this is the number of orderings of k elements from n objects. But now, we've got a lot of double counting here, because for each such choice of elements, we can, so if we choose k elements, we can order them in k factorial ways. This is something that we've just learned. So we have to identify k factorial of each choice. Okay, so we have to divide by k factorial. Okay, so this is the number of choices of k from, so k elements from a set with n elements. Good. So again, the formula is sort of a bit messy here, so we should, count this in a slightly nicer way. Well, on the bottom, instead of writing k by k minus 1 by k minus 2, we simply wrote k factorial. Okay, nice and easy. This almost looks like a factorial. Okay, so if we had n minus k minus 1, n minus k minus 2, all the way down to 1, this would be n factorial. Okay? So this is n factorial all over k factorial. But hold on a minute. We've introduced all these extra terms, so we should divide by those terms. And of course, what we've added is n minus k by n minus k minus 1 all the way down, or in other words, we've multiplied the top by n minus k factorial. So we should divide this by n minus k factorial. And so this is absolutely going to be the guts of the binomial theorem, and so we should introduce some nice notation, a slight shorthand for this guy. So we denote this by n choose k.